Good day, good morning, afternoon, evening. This is SI Sasha. Today we're going to look at this problem, and we'll just dive right in. The voltage across a parallel plate capacitor. All right, let's pause there and let's draw our parallel plate capacitor real quick. Nice and easy. Wire, plate, plate, wire. Great. Let's continue. Area is equal to 800 centimeters squared. Okay, let's convert into SI units. 0.08 meters squared. Okay. Separation is 2 millimeters. D is equal to 2 times 10 to the minus 3 meters. All right. And we have a function for voltage. Our voltage varies sinusoidally, has an amplitude of 15 times 10 to the minus 3 volts. And our trig term here is a cosine function, cosine of 150 t. All right, so this is the information we're given, and this is our setup. Now, what is a displacement current? Well, our formula for the displacement current says let's multiply epsilon naught times the changing electric flux. Now, note that when we talk about electric flux, we have to be referring to a flux measured through the area between these plates. So in other words, let's say I'm looking at one of these parallel plates head on like that, and the other plate is behind me. There's the wire going into the screen. There will be a changing electric field coming out of the cap like this. Why does that happen? Because if we look at one of these plates, there is an accumulation of charge out here, right? The charge is not able to just continue flowing through this wire and then get from this side of the capacitor to this side. It can't do that because to an electron, a distance of 0.0002 meters may as well be a light year, or the equivalent of a light year. That is a very, very great distance. So unless there was a very faulty capacitor here, in which case a short would come up, a short circuit, there is no way for that charge to get across. However, the accumulation of charge between the two plates will cause an electric field to appear, and a changing electric field produces a magnetic field like so, that loops around like this. And if you have a changing magnetic field like that, then what you'll have is a fictional current flowing across the two plates. So in other words, energy can still get across, and it will behave very similarly to just a natural current flowing through a wire. So in other words, how can there be a current through a cap without there being a current? Well, there is a current. It just goes in the form of fields from this plate to this plate. Now, keep in mind, again, it's the changing of the voltage that causes it. So the change in voltage causes a increasing electric field, which then induces a changing magnetic field encircling it, and that causes the flow of fictional current. And that's why our formula is epsilon naught times the change in electric flux. The change in electric flux and the change in the voltage are directly correlated. Okay, so we have a lot of this theory for this problem, but the best way to view it is we already have a formula derived for the displacement current. And yes, this works, but the changing electric flux piece of this would be a little complicated. We already have a formula for the current through a capacitor, and it's this. The formula through a capacitor is going to be the capacitance times dV dt. So in other words, C dV dt. Okay, and you're thinking, how do we get capacitance? Well, the good news is the capacitance is equal to epsilon naught times A over D. We're given A, and we're given D. So all we have to do is calculate it. C is equal to epsilon naught A over D is equal to epsilon naught times our 0.08 meters squared over our 2 times 10 to the minus 3 meters, and that'll equal 3.54 times 10 to the minus 10 farads, or about 354 picofarads. So that is tiny. That is a tiny, tiny capacitance. But that's not the point. The point is we're calculating our displacement current. The other piece of this is that we're given V of t, and that's equal to 15 times 10 to the minus 3 times cosine of 150t, but we're not given dV dt. All we have to do is take the time derivative of this formula, and we get 150 times 15 times 10 to the minus 3, get a negative sign, get a change in our trig term, 150t. Done. Take this, multiply it by the capacitance that we just found, which we found to be 354 picofarads. And what you get is one very tiny coefficient in front of the trig term that gives you your displacement current as a function of time. And that whole mess comes out to 7.79 times 10 to the minus 10 sine, and of course we have our minus sign here, sine of 150t, and this is measuring current, so we have units of amps. And that's the idea. We already know the formula for the current through a capacitor, and it involves taking a measure of the changing electric field, but the fact is C, which captures the geometry of the capacitor, and dV dt, which causes the changing magnetic field to induce our fictional displacement current, these are both built into that formula, which is why that allows us to say that is our current through the cap. So if there are any questions, please let me know, or first contact Professor Glenn, because he knows, but that is the idea here. Thank you.